Okay, half-life. All radioisotopes have a characteristic rate of decay measured by its half-life. I talked about the other day where my neighbor had this treatment done for cancer, and for a week, we couldn't bring, for 3 days, adults couldn't be around her, and for a week, kids couldn't be around her. And the reason why is she was radioactive. It seems odd to talk about a person being radioactive, but that is the truth. In fact, her dog had to go somewhere else. And the reason why is the fact that they had put in what are called radioisotopes into her liver, and those radioisotopes were emitting radiation in hopes of killing cancer cells, but they obviously do go outside of just that region. So if you're in close proximity to her, you're receiving doses of radiation that could be harmful. Why 5 days? Well, the half-life for whatever the radioactive material they use, which I'm not sure of what it is such that after 5 days of time, enough of that has decreased that she's no longer at the dangerous level to other people. Okay? Good question. Yes and no. Meaning, if you were to go into a nuclear power plant, absolutely radiation does stay on clothing. I don't believe for a person, they might actually give some recommendations like you need to wash your clothes or put them in a pile and wash your clothes. Like, for example, you probably wouldn't want your clothes, close to your children's room if you had this treatment, because there is some risk, but I don't believe that clothing gets enough what we're going to call exposure to really make that an issue. But in a radioactive plant, it absolutely does. Yep. Okay, so let's find out about this a little bit. Very interesting. This is used quite often, by the way. It's going to be used in more than just medicine, but quite often now, this treatment where you can go in with a catheter, okay, and they can actually then implant these seeds in various parts of your body where surgery might not be an option. So it's amazing that they basically go up through a vein, and then through this capillary, they're able to then implant this into the organ of interest, and try to help kill the bad and not harm the good to the point that it's devastating. A half-life is the amount of time needed for one half of the nuclei to decay to products. So you can just literally think of it's the time required to reduce the starting amount by half. So a quick example here. If you start with 100 radioactive nuclei, how many half-lives would it take to end up with 1.25 of the original? Now, 6.25 of the original. The easy thing about this is it's very simple if you just use drawings. So here's how it works. You start with 100, and you literally just break it down. So half of 100 is obviously 50. Break 50 down to 25. Half of 25 is 12.5, and half of 12.5 is 6.25. Now what you do is you count the arrows. The arrows represent what are called the half-life periods. And I'm going to actually draw that here because a lot of times people get these confused. These are called the half-life periods. So obviously you count them, and you can see here that it takes a total of 4 half-life periods to get down to the original, from the original amount down to 6.25. So 4 half-life periods. Now, the time of those half-lives depend on what isotope are being used. So this is where this table N comes into play. So if you can go to table N, it's one that we have not looked at this year. It's the last table, in fact, on our reference table, which is slap your neighbor on the back and say, hey, you made it to the reference table. Good job. Okay, now if you look here at table N, notice what you're given. 4 columns. You're given the nuclei column, which is basically going to tell you the mass and the chemical symbol. You're given the half-life, and you'll see that it's given in several different times. You have to be aware of that. You have D for days, Y for years, MIN for minutes, and S for seconds. So a lot of time if you're doing thyroid treatments, you're using iodine 131, and the half-life for that is 8 days. All right? MS would be
milliseconds.
It would be milliseconds. Where are you looking?
It's like the third one down.
Yeah, thank you. I skipped over that. MS is a millisecond. Extremely short half-life. Yeah, there's some that are years. Look at that one. That is 2.410 times 10 to the 4th years. Look at uranium. Super, super long half-life. 4.47 times 10 to the 9th years. So 4.5 billion years. Yep. So that's why that type of thing stays radioactive for so long. Next, you're going to notice the decay mode. And if you remember, if you forget what that symbol means, you are literally one chart away. Here's your notation if you forget where the decay mode comes from. All right, so that symbol, if you forget, B positive represents a what? Positron, good. Yep. Then you got the actual name, so gold 198, iron 53, the name of the nuclei. Okay, so let's pick a few. Please tell me, if you would, the half-lives for the following. Carbon 14, francium 220, and uranium 238. So if you would, look on table N and find then the half-life for those three. Just yell them out. 5,715 years for C14. Okay, francium 220. 27.4 years. Oh, sorry, seconds. Seconds. Very quick for francium. And then uranium 238.
4.47 times 10 to the 9th years.
Very good. 4.47 times 10 to the 9th years. So you can see there's a huge range in the actual time it takes to decrease by half. Half-lives are always constant. They are unaffected by external conditions like temperature, moisture, pressure. Those don't change the half-life. For right now, to keep us on talking about this radioactive decay, what I want to do is take you over, skip a page and go here, because it kind of goes in better with what we're talking about. Okay, radioactive substances decay at a constant rate, we just kind of mentioned this, that is independent of temperature, pressure, or humidity. We've already kind of mentioned this. The time it takes for the half of the atoms in a sample to decay is called, again, the half-life. And the shorter the half-life of the element, the less stable that element actually is. So something like francium that decays in seconds is very unstable. We've already done this, so you know where to look. I'm going to skip us right down to our first example. The following diagram represents the amount of a 1 gram sample of C14 that remains after 3 half-lives. So if you think about this, let's just say that this block represents 1 gram sample of C14. We already found out that the half-life for C14 is 5,715 years. So now the amount of sample that we would have after 5,715 years would be 0.5 grams. This would be in the first half-life period that we would go from here down to 0.5. In the second half-life period, we're going to take that amount and we're going to cut it in half again. What are we dealing with? 0.25 grams. And we've gone another 515 years to get there. This is the first half-life. This is the second. And then when I say half-life, I should say first half-life period, second half-life period. Now we're down to the third half-life period in this, and we will cut this last chunk in half. We are down here to 0.125 grams, which is 0.25 divided by 2, and we've gone another 5,715 years. Okay, so what I really want you to recognize is if you want to know how long it takes to do that, add them up or just multiply your half-life by the number of half-life periods. And that's what I usually do to find how long. Take your t to the 1/2, which means your half-life, time 1/2, and multiply it by the number of half-life periods. That will always tell you the total time it takes for that decrease to occur. So in this case, you're going to take 3 times 5,715, and you will get 17,145 years. This part is taken off the reference table, so you can get rid of it. Okay, but that equation is really important. How long your total time is given by the number of half-life periods multiplied by one half-life. Sophia. Gone. You know what? It doesn't ever completely go. It's like a mathematical question. You know, if you take a stick and keep chopping it in half, you never get to nothing. So no, they won't ask that. Most chromium atoms are stable, but Cr51 is an unstable isotope with a half-life of 28 days. What fraction of a sample of Cr51 will remain after 168 days? Now we have our equation that says basically time is equal to the half-life times the number of periods. Okay, that's the one that we just gave. To start this problem off, we are told that our half-life is 28 days. And we are told our total time, which is 168. That goes here. I need to, first of all, start this problem off by finding the number of half-life periods, because that tells me how many times I break the whole down by half.
Yeah, and you get 6.
Absolutely. So when you solve for number of half-life periods, you get 168 divided by 28, and you get 6 periods. Now, they don't even tell you the starting amount. So pick something easy. Pick 100 or pick 1. I'm going to pick 100. And we're going to take 100, and we're going to break it down 6 times. Ready? 100 go to 50, to 25, to 12.5, to 6.25, 3.125, 1.5625. In this problem, we broke it down 6 times by dividing each one of these by half 6 times. We got down to this amount. But this doesn't actually answer the question yet. That is the amount that would remain. But they don't want the amount, they want the fraction of the sample. What do I do? Yes, take this amount and divide it by your starting amount. So we're going to take 1.5625, we're going to divide it by 100, and this will give us our fraction remaining. All we actually have to do is divide the decimal place by 2, so we get 0.015625. That represents the fraction of the original that remains. Sometimes they'll ask for fractions. Sometimes they'll just say what's the amount that's left over. If it's a fraction, it won't. If they ask for an amount, it'll be in mass. Now in this next problem, which deals with the same isotope, this time it will ask for the mass remaining after 168 days, but they give us here a starting amount. So we know that after 168 days, we're going to have 6 periods. This time we're going to take 52 and we're going to break it down in half 6 times. Okay, 52 goes to,
26,
which goes to,
13,
which goes to,
6.5,
and
3.25.
that's going to be
That's 4.
4. 2 more.
1.625.
Good. And
0.8125.
great. And that's it. We've just broken it down. Kaylee did it for us on our calculator, and we again chopped it down 6 times, and we end up with 0.8125 grams. That is our answer. The one good thing about these problems is once you do a few, they look complicated, but they're really not. If you remember your equation, time is equal to the half-life by the number of periods, you can really figure out anything they're asking for. Please try this one on your own. Recognize that you're going to be working backwards. It says how much CR51 was present originally in the sample if you have 0.75 milligrams remaining after 168 days. We know that 168 days divided by 28 is still going to give us 6 periods. So now you're going to start and work backwards. You're starting with your initial amount and you're going to build it up. Don't divide by a half, or don't divide by 2. What are you going to do? Multiply by 2. So start with 0.75 milligrams. That's going to go to 1.5, to 3, to 6, 12, 24, 48. So that means you had to have been starting with 48 milligrams of your material. Go ahead and do the next one. How many half-lives would it take for a 100-gram sample to decay to 6.25 grams? This time you're going to just break it down. There's no math involved. You have to tell me the number of half-life periods, or the number of half-lives. Are you done, Madison?
Yes.
Hold on just a second, and I will have you do it for us. Okay, Madison, starting with 100, go ahead.
50,
Yep,
225,
yep,
12.5,
and
6.25.
great job. So you now count your arrows for the number of half-lives, and you obviously get 4. Okay, they like to ask you problems in this section about radioactive decay in terms of a graph. And what they usually will do is give you what's called decay events on your y-axis versus a time. And this time could be in days, it could be in seconds, years, or even milliseconds. For the number of decay events here, let's say that we set up a graph by 100s here. So we'll go up on our y-axis by 100. So 100, 200, 300, 400, up to 800 here. And then let's go by tens on our x-axis. So 10, 20, 30, 40, 50, 60, 70, 80.
Did you go to just 80?
Yeah, I went to 80.
Can you move it just for a second so I can see?
Yeah.
Okay.
I'll just move it up. Okay, now, and it says when the decay events of a sample is graph versus time, the half-life can be determined. So let's say that they give you a graph that looks something like this. We'll say 810, 620, 430, 350, 280. And what you're going to notice is that when you have half-lives, you're going to get this indirectly proportional graph that basically comes down and reaches an asymptote like this. Can anyone from the graph see how to determine the half-life? How would I, by looking at the graph, be able to determine the half-life? You're on the right track, but it's not 30. It doesn't really matter on the graph where you start, but you have to pick a point and record the time, and then go to a spot that is half of that original point and record the time, and then subtract the times. So let's start right at the beginning. If you come straight down here from 800, we know we put it at 10 days. And then if you come over here to half of 800 or 400, so I'm going to come across from 400 right down here, and we have it at 30 days. So we are going to subtract the difference on this graph of 30 minus 10, and we would get 20 days for our half-life. You could go 600 down to 300. If you did that, you would go basically 600 is at 20, 300 puts us about at 40, and you again would get 20. So it doesn't matter where you start on the graph, you're always going to get the same value. So you just pick an original amount, cut it in half, and then figure out the times that those correspond to, and that's how you do it. Okay, now there are a specific couple of these that you want to know about. The first one is using these isotopes to date things. Carbon-14 is an isotope, thank you, that is used to date, anyone know from your definitions? Yeah, used to date organic matter or basically once living substances. We get C14 into our body as you eat plants. Plants, require carbon dioxide from the air during the process of photosynthesis. And so in the environment, there's C14. And so some of that C14 is used in plants in their process of respiration during photosynthesis. We then consume the plants, so even if you're not a herbivore, you get C14 in your body. That C14 decays by half. The amount that you have in your body decays by half every 5,715 years, and they therefore can measure out, if they find a pile of bones, how much C14 is in them compared to how much is in the atmosphere. That gives you your starting amount, your ending amount, and they can calculate the time that object was here for. Rocks and non-living matter are typically using a different isotope, which is uranium-238. All right, so this is used to date non-living things. Obviously, the C14 has a half-life of 5,715 years, whereas the uranium-38 has a very long half-life, 4.5 times 10 to the 9th billion, well, 4.5% of the 9th is 4.5 billion years.
It's to the 9th.
It just didn't show good. Chemical tracers are radioactive material which are used to basically trace through your body or through a plant. They allow you to mark where something goes in a system. Radioactive P31 is used in fertilizers because phosphorus is taken up by plants, so you can actually determine where in the plant the phosphorus is used. In industry, because gamma rays have a high penetrating power, they can be used to measure the thickness of different materials. So you can actually take a gamma ray gun and figure out how thick a concrete wall is without knowing what's on the back side of it. And we'll pick it up there. Homework tonight, half-lives. It'll be very much like the problems we just did. Acid and bases is due tomorrow.
Huh?
Due tomorrow.
Oh, they're both in the room?
Both due tomorrow. Yep.
Acids and bases shows only like 15.
Yep, there's 15 questions for acids and bases, and then a few more for the multiple choice on the other. Have a good day, folks. Still turkeyless.